This is AP Calculus 4-5, Part 2, Related Rate Word Problems. A conical tank has a height of 100 feet and a radius of 50 feet. The height of water in the tank is falling at a rate of 2 feet per hour. How fast is the tank losing water when the water height is 10 feet? So in this example, we need to talk about what they've given us and what type of situation this is. So it's a conical tank. So a conical tank is the shape of a cone. So I'm just going to do a rough sketch here. Here's my cone-shaped tank. We've got a radius, and they tell us that the radius is 50 feet when the height of this cone is 100 feet. So if you think about that, any cone inside of the large cone here, wouldn't it be proportional to the entire cone? That's going to become significant as we do the problem, because if you notice, the radius here is half of the height, and that's going to be the case anywhere we have a radius and a height. That proportion will be the same because they're similar figures. And so we'll talk more about that later because we're going to have too many variables in this problem. And this happens a lot with cone problems. And you'll see what I mean in just a few minutes. Now, if you think about it, a conical tank, we're talking about the volume. They want to know how fast is the tank losing water. So they're asking us here to find the change in volume over time. So they're asking us to find dV over dt. And they want us to do that when the height is 10 feet. The water height is 10 feet. So we'll just say the water height right here is 10 feet. They say here that the height of the water in the tank is falling at a rate of 2 feet per hour. So they've given us dH over dt is 2. And if it's falling, it's a negative 2. Because when it's falling, it's decreasing. So that is important to understand when to put a negative in for a rate of change and when to put a positive in for the rate of change. The volume of a cone is 1/3 pi r squared h. We know we want to find dV over dt. So when we first look at this problem, it's very tempting to go ahead and take the volume by doing the derivative implicitly. And if you notice on this side, we've got an r squared and an h. So we've got basically 3 variables in this problem: volume, radius, and height. Now, if you look at what we've got here, they've given us volume, height, and the change in the height. Nowhere in this does it mention anything about our radius other than that the radius of the conical tank is 50 when its height is 100. And so just looking at this at first glance, what I'm going to probably try to do is take the derivative implicitly. Now, don't write this down because I'm going to erase it, but I want you to see why this won't work. If I take the derivative of this implicitly, dV over dt is equal to, now we have to think about this as the product rule. So there's the first thing, here is the second thing. So if I take the derivative of the first part, I would have 2/3 pi r times dr over dt, we're taking it implicitly, times the original second thing, h, plus the original first, 1/3 pi r squared, times the derivative of the second, which would be dH over dt. Now, if we go through and try to solve this problem with what we've got, notice we are not going to have all the information we need. We're trying to find dV over dt. We could plug in what we know, 2/3 pi. They didn't give us what the radius is. When the height is 10, but we know that if this is proportional here, then this radius also has to be proportional. So we can figure out that that radius is going to be 5 at the particular time they're talking about. And they don't tell us anything about the change in radius. They give us dH over dt, but there is no change in radius. So we don't know what dr over dt is. We can't plug in for that. The height at the problem, or at the instant they're talking about, is 10, so we can plug 10 in, and then if we plug everything else in that we know, we've got pi, we know r was 5, so r squared is 25, and then dh over dt is -2. So we've plugged in everything that we know, but there's a problem. We're trying to find dv over dt, but look, we have two variables that we don't know. And unless we have two equations, there is no way to figure out what this other variable is going to be. So doing it this way is not going to work. We have too many variables that we cannot replace. So I'm going to have to go back to the drawing board and start again and try to think about this problem a little bit differently. And this is a common thing that we're going to have to do when dealing with related rates. If you have too many variables to plug in for, then you have to have another way of doing that. So if we think about what they gave us, we know that we can't have a dr over dt. So we have too many variables in this problem to be able to solve it. So I want to find a way to get rid of the r variables here because they gave me h and they gave me dh over dt. So I need those variables in my equation. So there's got to be a way to get rid of the r. And if you think about it, this radius is 50 when the height of the original cone is 100. So the radius is 50 when the height is 100. We can use this to figure out a proportion that is equivalent to what we have here that will apply to the entire problem. So I know that r, if I just work through this proportion, that's 1/2 times h. So r is 1/2 times h. If I know that's what r is, based on what they gave me, I can replace r with what it equals over here. So let's do that. I'm going to replace this and say v equals 1/3 pi times 1/2 h is h over 2. That's squared times h. So what we have here is the volume now. Our new formula for the volume is 1/3 pi times h squared over 4 times h. So couldn't I rewrite this as the volume equals pi over 12 times h cubed? Isn't that formula much easier to take the derivative of than the original formula? So now if I'm trying to find dv over dt, I take the derivative. 3 times pi over 12 is pi over 4, h squared, and then we take the derivative implicitly, so we need a dh over dt. And at this point, if I'm trying to find dv over dt, all I have to do is plug in what I know. So dv over dt is equal to pi over 4, h at this instant was 10, so we have 10 squared. dh over dt was -2. So if I use my calculator to multiply all that together, dv over dt is equal to 100 times -2 is -200, divided by 4 is -50 pi. And my unit of measure, well, if you think about this, this is the rate of change of volume. The unit of measure for volume is, in this case, feet cubed, because it was 50 feet by 100 feet for the original cone. So the change in volume would be a -50 pi feet cubed per hour for my unit of measure. So the rate that the tank is losing water is -50 pi feet cubed per hour. Air is being pumped into a balloon so that its volume is increasing at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So we're talking about a spherical shape, a balloon. So if I just kind of do a rough sketch of a sphere, we'll say that that's my balloon. The air is being pumped into the balloon. So the balloon is expanding. It's getting larger, being blown up, and it's increasing at a rate of 100 centimeters cubed per second. So that means the change in volume, dv over dt, is 100 centimeters cubed per second. And it's asking how fast is the radius increasing. Okay, so they're asking us to find dr over dt, and they're giving us that the diameter is equal to 50 centimeters. So they're asking us how fast is the radius increasing when the diameter of the entire spherical shape is 50. Well, the formula for the volume of a sphere is v equals 4/3 pi r cubed. So if we're trying to find dr over dt, we would need to take the derivative of this function. So dv over dt is equal to 3 times 4/3 is 4 pi r squared times dr over dt. So we've taken the derivative implicitly, and then we need to plug in what we know. Well, dv over dt is 100. We've got 4 pi. We don't know what r is, but we do know that the diameter at the instant we're talking about is 50 centimeters. So we know that radius is half the diameter. So the r they gave us is 25. So I'm going to put 25 squared. And then we're trying to find dr over dt. So if I do the math here, I'm going to end up with 1 over 25 pi as my dr over dt, and you can use a calculator to get that information. You do 25 squared, that's 625, multiply that by 4 pi, and then divide by what you get here on this side. You end up with 1 over 25 pi. And so now we need to know the unit of measure of this dr over dt. The radius is a length, and the length that we're talking about here is centimeters. So the dr over dt is equal to 1 over 25 pi centimeters per second. You may remember this problem from the last section that we did. This one, we had the right angle here, and the ladder was leaning against the wall. This is my right angle. And before we used the Pythagorean theorem to solve this. But now the information that they give us here is a little bit different. The ladder is still 25 feet long, so it's still not going to change. I think in that problem we labeled this side as A and this side as B. And they've told us here that the base of the ladder is pulling away from the wall. That's still the same. So they're telling us that dB over dt is 2 feet per second. They ask us to find the rate at which the angle between the ladder and the wall is changing. Well, the angle between the ladder and the wall is this angle right here. I'm going to call that theta. And they're telling us that the ladder is 7 feet from the wall at the time that we're talking about. So they're giving us that B is equal to 7 at the instant of time that they're talking about. So if we're trying to find the change in theta over time, then we're going to be dealing with a trig function here. And we're going to be talking about this trig function as it relates to this side B and this side A. So if you think about the trig function that we have to talk about, this is a right angle, theta is this angle here, and B is the opposite angle, A is the adjacent angle. So I'm going to be talking about tangent of theta being equal to the opposite, or B, over the adjacent A. And if I'm trying to find the change in this angle, aren't they asking us to find d theta over dt, so the change in the angle over time? And you're also going to have to think back to the problem that we did before, because when we take the derivative here, we have two variables. We're going to have to use the quotient rule to find the derivative, and when we do that, we're probably going to need to know what both dB over dt and dA over dt are. So if you think back to that original problem when we did this, wasn't the change in A found to be, or dA over dt, found to be -7/12 feet per second? So in case we need that, I'm going to just pull that from that last example that we did, or that one example that we did in the last section. So if I take the derivative of this implicitly, tangent of theta, the derivative of tangent is secant squared. So I have secant squared theta times the derivative of theta, which would be d theta over dt. So we took the derivative of the left-hand side implicitly. To take the derivative of the right-hand side, we need to use the quotient rule. The derivative of b is dB over dt times the original bottom is A minus the original top, which is B, times the derivative of the bottom, which is dA over dt, and that's all over the bottom squared, which would be A squared. So what they're asking us to find here is what is d theta over dt. D theta over dt is what we're going to get by itself. So if I simplify this a little bit, well, if I divide this and this by a squared, I'm going to leave the secant squared over here right now, I would have dB over dt times 1 over a minus b over a squared times dA over dt. And then if I want to get the d theta by itself, or the d theta over dt by itself, I'm going to take this and divide by secant squared. Now, in reality, if I'm dividing this whole thing by secant squared, aren't I dividing it by secant squared over 1? And if that's the case, then wouldn't d theta over dt be equal to, since secant squared over 1 is just, if I invert and multiply, that would be 1 over secant squared times what's on top. And 1 over secant squared is cosine squared. So in reality, d theta over dt is equal to cosine squared theta times everything on the numerator here. And at this point, I'm going to plug all of these numbers in that I can find. So d theta over dt is equal to cosine squared of theta. Well, cosine of theta is adjacent over hypotenuse. So the adjacent is 24, the hypotenuse is 25. So cosine squared of theta would be 24 over 25 squared. dB over dt is 2. 1 over a would be 1 over 24 minus b was 7 over a squared, and I'm just going to write that as 24 squared. And dA over dt was the negative 7/12. I'm going to take all of this and put it in my calculator. And when I do that, I get d theta over dt equals 1/12, and that is going to be radians per seconds. So the rate of change for the angle between the ladder and the wall is changing at a rate of 1/12 radians per second. A man 6 feet tall walks at a rate of 5 feet per second away from a street light that is 15 feet above the ground. At what rate is the tip of his shadow moving when he is 10 feet from the base of the light? So to draw this one, you've got a lamp post here. It's 15 feet tall. You have a man walking in this direction away from the street light. The man is 6 feet tall, and he is casting a shadow from the street light. So his shadow would be down here. Now, we know he is 6 feet tall. We know this is a right angle. So we know the big triangle is going to be proportional to this small triangle. So we're going to use proportions to help solve this one. So a man 6 feet tall walks at a rate of 5 feet per second away from the street light. So he's walking in this direction at a rate of 5 feet per second. At what rate is the tip of the shadow moving when he is 10 feet from the base of the light? I'm going to let this length right here be my x. I'm going to let the length of the entire large triangle be y. If 6 is proportional to 15, I'm going to use that to help me solve and find what they're asking me to find. So if 6 is proportional to 15, then wouldn't y minus x, this right here would be y minus x, be proportional to the whole thing, y. So if they gave us that he is walking at a rate of 5 feet per second, wouldn't that be the change in how fast this is changing? So that would be dx over dt is going to be represented by 5 feet per second. So if that's the case, I'm going to take the derivative of this implicitly. Now the easier thing to do would be to go ahead and cross multiply. So 6y equals 15y minus 15x. If I get my y's together, 6y minus 15y is negative 9y equals negative 15x. And then to make the math a little bit easier, I'm just going to go ahead and get y by itself. Negative 15 divided by negative 9 is 5/3. So y equals 5/3 x. So if I'm trying to figure out what rate that the shadow is moving, so they're asking us to find, or how fast this dy over dt is increasing. They want us to find dy over dt. So if I take the derivative, dy over dt is equal to 5/3 dx over dt, and so dy over dt is equal to 5/3 times 5, leaving me with dy over dt is equal to 25 over 3 feet per second.